Okay, this is an interesting problem. We've got this charge Q here spread out along this little rod of charge here that has length A. We are going to find the electric field somewhere along the x-axis at a point X away from the origin. Okay, the key to this problem here is we're going to define right here, we take a little slice of this, call that a little delta x. And then we're going to define the distance from that slice to x we're going to call r. So r here will be this distance minus this distance. Or more importantly, when we go to write our integral, r is going to go from x to x minus a. This total distance is x. This distance in here is x minus a. So those will be our limits of integration. Okay, so here in our little delta x there, we want to find our delta q. Remember, delta q is always charge density times your delta distance, whatever that is. So our charge density, lambda, is total charge divided by total length. So delta q will be lambda times our length, delta x. So that's lambda q over a delta x. Now, I'm writing delta x, but I know I'm going to be integrating with respect to r. But notice here, as x changes, so does r. So delta x and delta r are interchangeable. We just got to be careful with our signs when we write our integral. So I'm going to replace my delta x with the delta r, because that's going to be my variable of integration. Okay, then the electric field from that little tiny sliver of charge is always k, the amount of charge in that sliver divided by the distance squared. The distance we defined as r. And this all points in the x direction. We can see here, I've got a bunch of positive charge here. Every single little tiny sliver of charge is going to create an electric field that points to the right. So I don't have to worry about y components and x components. This is all x component. All going to point to the right. Okay, so then E total will just be the sum of all of these EIs. So that's the sum of k lambda q over a delta r over r squared. I can just stick my r squared in here. I take the limit as delta r approaches 0, meaning we're taking an infinite number of slices, n going to infinity if I want to think I equals 1 to n. And then this sum becomes an integral. E total will be the integral of k lambda q over r squared a delta r. Now we got to be careful with our limits of integration. We're going to think backwards here. We're going to think we're integrating from smallest to biggest r. So my smallest r, I'm integrating that way. Looks weird, but that's how I capture more and more charge as I go. So even though x goes that way, I'm integrating backwards. Smallest r here would be x minus a. The biggest will be x. So we get this integral. So we know we're going to end up with an x in our answer. This is a weird problem, because the x doesn't appear anywhere in the integrand. I'm not integrating over x, I'm integrating over this variable I made up called r, and I'm going to pick up my x's from my limits of integration. It's a weird way to set up the problem, but it's much easier. If you try to set this up so that you can integrate over x, it becomes a very difficult problem. I've worked this problem 3 or 4 times, trying it both ways, and by far this is the easier way to work the problem. Okay, so we just do the integral. The k, the lambda, the q, the a, those all come out. Oh, well, the lambda up here, lambda was q over a. So delta q here should have been q over a delta x. There's no lambda in here. We already have the lambda. That's the q over a. Sorry about that. So pull out the stuff that's constant. K, q, a can all come outside. This is a dr. And we have the integral of 1 over r squared dr, evaluated from x minus a to x. Antiderivative of 1 over r squared is negative 1 over r. So this will be kq over a negative 1 over r, evaluated from x minus a to x. And at first that might bother you, having a negative 1 over r, because we know we're going to get a positive electric field, but we'll fix that here. So this would be kq over a, top minus bottom, negative 1 over x minus a negative, so plus 1 over x minus a. This number is smaller, making this fraction bigger, so this is actually a positive number. This fraction is bigger in absolute value than this one, so this is a positive number. So we get the electric field, points all in the x direction, so we'll write this as a vector, and we can distribute there if we want, kq over a x minus a minus kq over xa, comma, the y component is 0. And of course, our units, we should put units in here, newtons per meter.